to Chao, who works at MSIN at Monash with us. And I think Chao said already that he did his PhD in a clinical trial in mild cognitive impairment. He used a variety of imaging techniques, but spectroscopy, which is actually like the ugly duckling of imaging, the elephant man, if you like, which we love, very keen to push forward with it. He's going to talk a bit about that and see if he can convince you that this is good as well.
Okay. Let's wait this projector to warm up.
Sometimes it's a bit temperamental, this projector.
Yeah, so I'm going to talk about the spectroscopy, the beauties and the ugly. I know it's going to be a tough presentations because all the beautiful pictures have been taken by all the presenters and leave only the spectroscopy, which is black and white, very dry things. It's like the dwarfs compared with the Snow White, but actually these small creatures can tell us a little bit more secret about the brain. So I'm going to start with a brief history of spectroscopies and then some basics, then followed by how to process the data and application, etc., and wrap up. So it's a brief history about this magnetic resonance spectroscopy, MRIs. MRIs is like one of the families of all the other MR technologies, which is originally from the NMR concepts, which is the first. The start was labeled by Professor Rabi first observed the magnetic resonance phenomenon. And in 1945, Professor Bloch and Purcell established the nuclear magnetic resonance spectroscopy, and later on this technique transferred into spectroscopy, which is I'm going to talk about today. And then in 1973, Professor Lauter produced the first NMR imagings using NMR technique, and then this later on was transferred into the MR imaging for medical use. And later on we have the function MRI and the DTI techniques later on, and then we have our Snow White. So from this picture we can see that spectroscopy is at least 28 years older than Snow White. But spectroscopy was originally designed to do the quantitative measurements, so which is very important for this technique. And because spectroscopy was targeting all these metabolites, which is interesting for some biomedical models, so make it even more and more popular recently. So because this start at the beginning, I'm going to talk a little bit more about the physics of spectroscopy. Hope it don't get people boring. So the story starts with the magnetic M. So we know that a rotating charged particles, we can consider that as a magnetic bar. So let's take the hydrogen proton, for example, and for my whole talk, when I'm talking about protons, it's the hydrogen protons, not the proton from other nuclei. So if it's rotating in this way, and we can consider it as a magnetic bar, which is pointing upwards. And if we consider the protons in the tissues outside the scanners, the direction of these small magnetic bars can be randomly pointing everywhere. And if we put the tissues into the scanner, the protons will line up with the external magnetic field. So there are two states. If the direction is in the parallel direction with the external magnetic field, we call it low energetic state. And if it's in the anti-direction, which is, we call it high energetic state. So if it's so hard to understand, we can take we can consider of people. So if I consider the whole classroom as a teacher, and each of you is the protons, and my talk about physics is external magnetic field. And every of you will be into the two status, low energetic status, sleepy, and at high energetic status. And the proton is similar like people, lazy, and my talk is like magnetic field, it's boring. So we find more sleeping people in the tissue rather than energetic. Okay, so that's the first step of MRI. The second step is we call it excitation, so we call it wake up. So the wake-up signal is actually an RF pulse, so it's a radio frequency pulse. It only affects the sleeping people, and it's a very unique frequency. So for example, if we put in 1.5 Tesla scan, if we want to wake up a proton, we need to give it an alpha pulse of 63.855 megahertz, and only this frequency will work. So it's like a resonance, others won't work. So we have to carefully select this radio frequency so I can excite the protons we want. And we give it to excitations, and some of people wake up. And once it wake up, we switch off the wake-up signals, and we come to the third important phase, which is relaxation, getting relaxed. So remember the person who just wake up, you want to go back to sleep. Why? Because of the external magnetic field, because of my talk. I'm still talking about physics. You wake up, it's still physics, let's go back to sleep, all right? So that means that he's transferred from a high energy state to a low energy state. But in the meantime, he releases the powers to the surrounding. And if we use receive coil to pick up the signal, we got a free induction decay signal, which is produced by the relaxation. And we put that in the Fourier transform, and we got a peak in the frequency domain. So we got one peak in spectrum. And we're only interested in those people who just wake up. Why? Because only those people will have the relaxation period, and those relaxation will produce the FID signals, which is a later on transfer into the useful signals. So then when we talk about these protons, give you a rough idea, so there's only part per millions of all the proteins in the tissue, but it still ends up with billions of billions proteins within the tiny little bit small part of the tissues. Okay, so now we finally come to spectroscopy. So how we get the spectroscopy? So the most important concept in spectroscopy is the chemical shift. That means different proteins will do the relaxations in different way. Basically means quicker or slower. So like someone wake up and fell asleep in 3 seconds, and someone wake up fell asleep in 3 minutes. And the things it and this process was dependent on the magnetic field around it. Okay, just make it easy to understand. We think about methanol. The carbon and oxygen nuclei also have their own magnetic field on top of that, of the external magnetic field. So then the hydrogens will have different local magnetic field for each hydrogen proton. So those three of them share the same type of local magnetic field, and they have a relatively longer excitation period. So it's considering like these three people is under air condition, and the chill weather just make them stay awake a longer time. And the blue one is in a different magnetic field, local magnetic field will give them a much quicker relaxation period. So for example, someone sitting in the sun is getting to sleep very quickly. And while they're doing this relaxation process, they will release the FID signals, which we can pick up using the receive coils. And after Fourier transform, we find shiftings on the frequency domain, so we get 2 peaks. And the blue peaks is indicating with the relatively faster relaxations, if you like, and the pink one is indicating another one. So then we got the shift on frequency domain, which is purely dependent on the relaxation period, and which is dependent on where they're located on the molecule. So that's why we call it chemical shift. And another important information from the spectroscopy is the area and the each peaks indicating the concentration of this type of proton. So if you look at that, the pink so the pink protons is 3 times more than the blue one. So if you look at the areas and the pink peak is 3 times more than the blue. The pink is bigger than the blue peak. And the second important, is also very important concept is the spin and spin coupling. That means the relaxation period is not only dependent whether you're sitting in the sun or air conditioning, also depends on your neighbor. So if all your neighbors fell asleep, you're more likely to fall asleep as well. So let's take ethanol for example. The same thing will have the chemical shift because the two carbons and the one oxygen will produce its own magnetic field and influence all the local magnetic field of protons. And they form three types of local magnetic fields: the blue, green, and the red one. So if I do the same things and we find the three peaks on the frequency domain. Okay, so the green one and the blue one are so close to each other, so they start to interact with each other. And the blue, so it's a contradict, so they interact with each other. And on the frequency domain, what you actually observe is this small splittings of the peaks. And then instead of you have one main peak, you have several peaks. And like the red one is so far away with the other neighbors, so you don't get any interactions. So it's only one peak for the red. This is boring, but it's very important this is the basics of a megapress, which give you the ability to detect something like GABA, so GSH, or separate the glutamine and glutamate. So let's give comparisons of all MRI images and the MRI spectroscopy. The MRI is mainly focusing on the water, and spectroscopy is on metabolites. And MRI is mainly targeting hydrogen protons, and MRIs, you have the options to target other nuclear. MRI have a very big concentration in terms of the hydrogen because it's from water, and the spectroscopy, you look at something really weak signal like a millimole levels. You get a beautiful MRI image because of the spin density, relaxation of water, and you get the spectroscopy because of the chemical shift we just talked about. And the MRI, you get beautiful and very fine structures. Spectroscopy, you're looking at a centimeter scale. And MRI, you can acquire the scan whole brain in seconds. Spectroscopy, you get minutes. And the outcome is obviously not as beautiful as MRI. But there were two types of spectroscopy. First is the single voxel spectroscopy, which is I'm going to talk about more later on. So that means you select a region of interest which your hypothesis is based, and you place the voxel there, you get spectroscopy from that region. And the second one is the chemical shift imaging. Is that you scan the whole plate and separate into each big voxels, and you can get spectroscopy for each voxels. As you can imagine, CSI is going to take more time, but of course the trade-off is to get that signal-to-noise ratio. So data processing. Okay, so what is the signal really looks like? So it looks like that. So what is this big one is actually the water. Why? Because the water is hundreds of millions more concentrated than the metabolites in the brain tissues. And remember, the areas under the peak is indicating the concentration. So we have this huge, big snow white, which is on top of our dwarf. So you can't really see the dwarf, it's hiding under the skirt of the snow white. So the first thing we like to do is to get rid of snow white. So we will apply the water suppressions, and then we can see our 7 little bodies here. And so this is, I pick up the 7 major ones. So there were 4 big brothers, which is NNA, choline, creatines, and I call it MI. And then some little one, lactate, and there's a twin brother, is the glutamate and glutamine. So the NNA is this one, this resonance at 2.02 ppm, and it's usually the markers of neural health. And the second one is choline, which I call it the bad, because the increase of choline always indicating the active tumor. And the third one is creatine, usually stable, so it always usually served as the denominator of creatine and choline. So the fourth one is MI, is used as glial cells markers, and the lactate is sometimes it's hard to detect in healthy subjects, but the increase of these markers usually indicated necrosis. And the glutamate and glutamine is always hard, usually hard to distinguish, and usually labeled as G or X in the reference. Okay, so to process data, first the straightaway thing is you can usually always get the signals on the MR console. So the radiographer will help you to process the data and tell you how big are all these, the peaks. What's the signal of the peaks. And the second one is LC models. It's a popular processing tools, but it's charged and it's not cheap. And the Tarquin is quite similar like a LC model, but just get a little bit less technical support. The good thing is free. And GMRUI is more powerful. It not only processes the spectroscopy, but also NMR. So when you set up GMRUI, you will need someone know it to set up for you. So talking about the data quantification, which is we want to measure how big our little dots are. So the first one we usually use is a relatively value. So because creatine is stable, so usually as a denominator. So in your publication, you can just talking about NNA on creatines or choline on creatine, that usually should be fine. And but creatine sometimes not always stable, so that's to come to the second thing is the absolute value, which is calculate the actual concentration at the region of interest in the peak, and basically use water intensity as the denominator. And it is more robust than the relatively value, as you imagine, but they need something extra. So for example, they need to acquire extra water intensity, which is usually included for GE scanner, but there's always a couple of seconds you can put it in. And the second one is you probably need to calculate the fractions of CSF. If you're using the traditional way, the relaxometry, you're probably looking at 10 minutes. But I have some script to run it to get the fraction of CSF using the T1 image you get and your spectroscopy. So it can save you some money and time. And it's also important because not only to doing the absolute quantification, but when you're doing other type of post-processing, you really want to get rid of the partial volume effect of the box you choose. So that is very important for all types of signal processing, for MRI spectroscopy processing. So my script is now working with Philips and Siemens scanner, and G scanner is on the way. I'm happy to share a script with you if you want to process the data, and it's going to be public once everything is finalized. Okay, so that's all about technical. Let's talk about the applications of MRI spectroscopy. The traditional application of spectroscopy is in brain tumor. So first is because spectroscopy can help to distinguish between abscesses and glioma. So for example, here you see a huge peak of cholines for this glioma, which I said is the bad, is indicating the active tumors. And for the abscesses, we don't have this, there's no cholines, but there's a big lactate, which indicates the necrosis. And the second big use is to MRIs can help to distinguish between the radiation necrosis and the tumor recurrence. So this is a patient with a history of anaplastic astrocytoma treated with surgeries and radiation. So the increase of cholines indicating that's actually the tumor recurrence. So when it comes to the cognitive neuroscience research, the NNA is usually to be the most interesting things because the high concentration of NNA was always associated with higher intelligence, as well as during the situation of conflict is indicating with the better task performance. So this is a project using both task function MRI and spectroscopy, looking at the roles of NNA doing this task. So the people is doing the subjects is doing the task into scanners, and all this yellow dots indicating the activations of anterior cingulate, which is introduced by this task. And the blue box is the region of interest of spectroscopy where we put in, and we can calculate the NNA of that regions. And by doing this structure equation modeling, so we can find this the NNA at these regions and at also anterior cingulate regions are linked with the intelligence, which is further associated with the activations of these regions as well as the performance of the task. There also can be, spectroscopy can also be used in psychotic disorders. These papers find the decrease of NNA for schizophrenia subjects at dorsals and rostral cingulate cortex on both hemispheres, and it's probably implying the neural loss or dysfunctions at these regions. And the similar results was found at the NNA concentration at the temporal lobe. So when we're comparing the ultra high risk psychosis with the healthy subjects, we find a decrease of NNA concentration on these regions. For Alzheimer's disease, also find the decrease of NNAs and multiple regions, as well as importantly for Alzheimer's, you also find this increase of MI. So usually the NNA on MI is biomarkers for Alzheimer's disease in terms of MR spectroscopy. So for cannabis users, also find this global decrease of NNAs of multiple regions for the cannabis users. And MR spectroscopies can also be used in deep depressions or other like Austin kind of disease study. And the more application, so we just talked, the application I just talked about is one of the 7 dwarfs like NNA or creatine or MI, but it's actually some other little creatures is under those 7 dwarfs like GABAs, like glutathione, and to separate the twins, glutamate and glutamine is very important as well. And all this can be done by using the megapress sequence, which is going to be established on our scan. And it's more important, interestingly, is you can use this MR spectroscopy to targeting the neurogenesis, and that is part of my PhD work involved. But however, I didn't have any results to share with you at the moment, what we do in the future. So let me conclude with about spectroscopy. So MRIs is old but powerful MRI tools to quantify the metabolites, and the new application of spectroscopy will allow us to quantify the other weak signals. However, the challenge of MR spectroscopy is exit. First is we might introduce a false discovery rate when the signal noise is low. So if we look at all this weak peak, we could false discover some of the results, overmodel the noise. And second, we need to predefine the regions based on the prior knowledge. That means before you start scanning, you have to think about your question is and just predefine the regions. And then you have to choose carefully when you're doing the data processing. And of course, the sequence is also the data is simple, the sequence is as complicated as other types of sequence. So set up the sequence correctly before you press the red button.
Should never press the red button.
Okay, so that's all my talk, and any questions?
Thanks. All right, any questions about spectroscopy or Walt Disney? You're welcome.
I have a relatively ignorant question. The final paper you showed was looking at hippocampal region, I think, and what's the spatial resolution? I mean, is it a similar kind of thing to other imaging techniques where they just, how do they isolate the area?
You mean the spectroscopy on hippocampus?
Yeah.
Oh, in spectroscopy, as I said, the spatial resolution is only centimeters. So you use the hope I answer your question, is use the structure image to find where the hippocampus it is, and you just place the whole big box.
Oh, okay, so it's the same thing, kind of just.
Yeah, overlap on that hippocampus. So you can't see the shape, but you get the spectroscopy within that box, which if you put on the hippocampus, that's from hippocampus.
It's an average of that, so all the way across the entire section,
Area.
the area that is placed, and it's also an average across intracellular and extracellular as well. So if you're looking at something like glutamate, it's kind of a combination of the whole
Of everything.
of everything, rather than separating out
Yeah.
intra versus inter. With glutamate you can, but you need better techniques.
But you're right, it's exactly that function where you're requiring structural first, and using that as a template to put the box on top of it. Structural is any imaging paradigm we start with structure.
Yeah.
Did you have a question?
I was going to ask about spatial resolution. So, I mean, how small can you get a box?
I think ideally 2 centimeter by 2 centimeter by 2 centimeter give you a decent spectroscopy. You can push it as small as you can, but you really push the limit of doing the shadings of the scanners, and also if it's too small, you get very less signal to sample. As I talked about, you're talking about something like millimole per liter. So if you think like 1 centimeter by 1 centimeter, I think that would be very limited.
Can you compensate with increased acquisition time?
Yes, of course, but like 128 average will cost about 5 minutes, and if you double that, you only have improved, theoretically improved like 1.7 better signal noise ratio, and that will double your time, it's about 10 minutes. And if you scan too long, the subject is moving by any chance, you introduce the moving artifact, which is, you don't want to have that.
So increasing your volume also increases your sensitivity to all the environmental things that might be going on. You know, whether there's a blood vessel or more grey matter or more white matter, each of those components obviously influence the metabolite, so you really amplify that effect.
Right.
So you've got to control that back.
But then you're perhaps bridging across functional regions as well as you increase. So I guess it's a balance, right?
We use stencing signals for NRS. Do you have much trouble with shunning? Do you find you have to do manual shunning as opposed to web shunning? I was looking at sort of shooting the neighbourhood sequence. I was wondering if we could do the same issues with that.
I haven't do megapress on our, so for the traditional sequence, I think automatic machines will do the work. And I have tried to scan some megapress sequence on the trial scanners in Swinburne University, and they use, the radiographer is doing very good shading. He's doing the manual shading, and we get some good signals from Phantom.
Depends on your scanner as well, I guess, depends on how good your magnet is.
Yeah.
Probably manual shunning for neighbours.
Yeah, probably. Yeah.
I might answer my question. So in terms of when you're looking at neurotransmitter concentrations, if you're looking at just a box, are you getting just sort of all the neurotransmitter concentration in there? So is it like any differentiation between like whether it's synaptic, extrasynaptic? It's just just everything.
Yeah, everything.
Yeah, I mean, again, with glutamate, obviously, if you can separate the peaks, one is intracellular, one is extracellular.
Yeah.
But beyond that, it's not really possible.
Yeah.
What are the known proton type spectroscopies? These phosphorus ones.
Yeah, that will. I think some of the phosphoron spectroscopies can easily pick up GABA signal, so it depends on the molecule that you're interested, whether they have some interesting shape. So you can choose the another type of the resonance spectroscopy technique. But usually, if you want to choose another one, you have to buy the specific coil from that type of nuclear. So it's usually extra cost of your experiment.
The signal goes down by a lot as well.
Yes, of course, the concentrations.
So you divide the RF coil.
Yeah.
Yes.
Receive and transmit.
All right, we might go to the next talk. Thank you, Chao.